Thank you and welcome everyone to the IEEE Professional Communication Student Society under the University of Moratuwa Student Branch Chapter. I'd like to briefly talk about professional communication and show you one technical aspect of communication in my brief presentation. First of all, communication has so many aspects that we need to think about. First of all, we must aim at clarity. Clarity, 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 says the famous Strunk and White Elements of Style book, then commonly attributed to Pascal. If I had more time, I would have written a shorter letter. Then from the same Professor William Strunk, we have vigorous writing is concise. A sentence should contain no unnecessary words, a paragraph no unnecessary sentences, for the same reason that a drawing should not have unnecessary lines and a machine no unnecessary parts. This requires not that the writer makes all sentences short or avoid all detail and treat subjects only in outline, but that every word tells. From the ProCom Society website, under Resources, medium need not determine the message. Also, from the same website, let data speak loud and clear. So you can see so many things are there about communication, but we will look at one aspect today by comparing two versions of presentation that I prepared. First version on gradient descent and moments. A way of minimizing an objective function effects by updating the parameters in the opposite direction of the gradient of the objective function. We move in the opposite direction of the gradient downhill until we reach a local minimum. Now, if we take the gradient of this objective function at xt plus t minus 1 as this one, and we designate that as gt, we move in the opposite direction. That's the reason for the negative sign, and eta is the learning rate. It determines the size of steps we take to reach a local minimum. Now, what is gradient descent with momentum? Adding a momentum to gradient descent solves the problem in ravine navigation and getting stuck at a local minimum. The momentum term increases for dimensions whose gradients point in the same directions and reduces updates for dimensions whose gradients change in directions. As a result, we gain faster convergence and reduced oscillation due to the momentum term. So we have the same equation that we saw last time. And if we add a momentum term to that, that means we keep track of the gradient, the previous gradients, in our mt term, and we move in the opposite direction of this mt with the same step size eta. Okay, now let's look at my second version. Now let's think about a two-dimensional function in x1 and x2. You can see it has two values. So I have drawn of this function a one-dimensional version for us to easily see. Now we start our optimization at some point. So you can see it's like a metal ball rolling downhill. And to do that, we compute the gradient. You can see the gradient is positive here. And we have to move in the opposite direction of this gradient. And that means we have to move in this direction. Alright, now we are at this point. This point obviously has a higher gradient. That means our step must be large in this case. And we recognize that the gradient is still positive and large. And we move in the opposite direction of the gradient by this much. So the step that we take is minus eta times the gradient of fx. So minus eta and gradient of fx make sure that we move in the opposite direction of the gradient, a step proportional to the gradient. And if we move in this fashion, hopefully we will reach this minimum where the gradient is actually 0 and will be stuck in this so-called local minimum where the actual global minimum is over here. So when we look at this gradient descent mathematically, we estimate the gradient at some point xt minus 1 and designate that as gt and move in the opposite direction of gt to get the new update of xt. And this one easily gets stuck at a local minimum as we saw in the diagram. But when we add the momentum term to the same equation, you can see we keep track of the previous gradients through this mt. So like a metal ball that has a momentum, it has some energy even when it reaches this local minimum, so that it has the power to escape the local minimum. So it builds up velocity or momentum as a running mean of gradients. So if we see that through an animation, you can see the cyan ball is gradient descent and the purple ball is gradient descent plus momentum. You can see the purple ball has momentum, so it has the power to go out of the local valley, which is here, and reach the global minimum. Okay, so in summary, what we looked at today is in making presentations, we must strive for clarity. For that, we can use infographics rather than text. But in any case, we must use carefully designed visuals so that we convey the correct message in a precise and clear manner. Thank you.